Welcome to the video for Chapter 21. Today we're going to talk about what happens when an electromagnetic wave encounters the boundary between two different types of materials. For example, between air and glass, or between one type of glass and another type of glass. Part of the wave is going to be reflected, part of the wave is going to be transmitted, but we're going to also begin by stepping back in time. We're not going to be talking about waves at first, we're just going to be talking about fields. We are going to discuss what happens when an electric field hits the boundary between two materials, what happens when a magnetic field hits the boundary between two different materials. We're going to see how the direction of the wave changes, and we're going to see how we can then apply that into the study of electromagnetic waves. Our historical perspective today is to point out that although Snell's law is named after Willibrord Snellius, I imagine he got picked on for that name, the law was actually first discovered by Ibn Sahl in 984. He was a Persian mathematician in Baghdad. He built on the work of Ptolemy, and he was the first, people have referred to him as the first scientist. He was the first person to understand the behavior of lenses and parabolic mirrors. So I just wanted you to know Snell's law, kind of a misnomer, should have been called Sahl's law. So let's talk a little bit about boundary conditions. We understand how waves propagate through free space. We understand how waves propagate through a dielectric, but what we don't understand is what happens at the boundary between two different types of dielectric materials. Those questions, it turns out, are extremely important. You know, if you wear contact lenses or eyeglasses, everything we're talking about today is going to be extremely important to you, because the optics in those glasses, or the optics in a camera, or the optics in a telescope, or whatever it is that you're working with, all of those are going to have the foundation in the laws that we're talking about today. And although we do think of optics as its own field, optics is simply a subset of electromagnetic field theory. We'll let them have it as their own field, but we understand that it's really built on electromagnetic field theory. So what we're going to do is we're going to first of all talk about an electric field and a magnetic field at the boundary between two regions. And each one of those electric field and each one of those regions has its own value of relative dielectric constant, relative permittivity, and also of the magnetic field relative permeability. And so what we want to know is what happens at the boundary. Let's first of all simplify things by considering just the field that is perpendicular, which we'll also call normal. I want you to understand that normal here is a word that just means perpendicular. We're going to just consider the normal components first, and then we'll talk about what happens at the tangential or parallel components in just a little bit. So here you can see a picture that we have a normal component of the electric field. We're representing this by D, and because there's a dielectric, and then also of a magnetic flux density B. So there's the normal component in the first material, and then there's the normal component of each of those in the second material. And the question is, what happens? Is it continuous? Does it increase? Does it decrease? We can apply our Maxwell's equations to be able to answer those questions. So we're going to start out by considering Gauss's law. You'll remember that this is our form of Gauss's law. Way back in Chapter 8, we originally introduced this law. And what we can do is we can take a Gaussian surface right at the boundary. So this dotted box that I'm showing here in figure 21.1 is a three-dimensional box. It's encapsulating a portion of the boundary here, and although we can't really see it, there is a third dimension here, and this third dimension is sort of going off in this direction, and that third dimension has a surface area of delta S. So we're just looking at a one-dimensional sort of component of this, but there is a delta S, and so we need to account for that. So we understand that there's a portion of the electric field that's flowing in, and there's a portion that's flowing in, and that's D1 sub n is flowing in, and D2 sub n is flowing out. But you'll remember that when we're talking about surface integrals, flowing out is positive, flowing in is negative. So that's why this is D sub 2n minus D sub 1n, because outward is positive, inward is negative. Then that's multiplied by the delta S. We're going to assume that sandwich is extremely thin, so there's nothing coming out of the edges. And then we're going to say, well, there's the possibility that at that interface, there could be, just right along this boundary, there could be a rho sub S that exists right on that boundary. And if that's true, then it's possible that there could be some charge that is creating electric fields that is perhaps impacting this result. So what we find is equation 21.1. We can cancel the delta S's on both sides, and we get equation 21.2, and that equation is 100% true for all circumstances. But most of the time, rho sub S is going to be equal to 0. And so if there is no surface charge density, we're going to say rho sub s is equal to 0, and that's our assumption. That's not, we aren't proving that. We're just saying that in most cases that's true. And if that's true, then d sub 2n minus d sub 1n equals 0, or d sub 2n equals d sub 1n. So we're going to do 4 cases, and this is our first of those 4 cases. We can also remember that the displacement field is related to the electric field by epsilon r times epsilon 0 times E. And so we can write an equivalent form of equation 21.3 right here in equation 21.4. And notice, for example, that if you knew E sub 1n and you wanted to know E sub 2n, well, you could say E sub 2n is equal to E sub 1n times epsilon r1 over epsilon r2. So it's possible that although it didn't get a box, that this equation is actually more valuable than equation 21.3 if what you have is the electric field E rather than the displacement field D. Now we're now going to take Gauss's law from magnetic fields, which is just to say no magnetic monopoles. So we understand that's from chapter 11. I always like to recopy these equations so you don't have to go back and look at them, but I also want you to know I didn't just pull this out of the air. We proved and or demonstrated and or assumed this equation way back in the previous chapter. So we can do the same analysis here. B sub 2n minus B sub 1n times delta S has to be equal to 0. And in here we aren't going to make any assumptions about whether or not there's a surface charge density or anything. That doesn't matter. We can just say divide both sides by delta S, and we're left with equation 21.6. And that gives us the relationship in the magnetic fields at the normal components of the magnetic fields at the boundary. We can, of course, then rewrite them in equation 21.7 in terms of h sub 2n. And so again, for example, you could say h sub 2n is equal to h sub 1n multiplied by mu sub r1 divided by mu sub r2. And that might also be a very useful form of the equation. Now let's consider the tangential electric and magnetic fields. Each of these 4 cases isn't super hard, so I'm going through them fairly quickly, but the results are going to be important when taken together. So now we're looking at a picture in which this dotted line is no longer representing a box. It's no longer a 3-dimensional shape. It's a 2-dimensional path. And so what I've got here is a path where, let's go counterclockwise. So I'm gonna take the path to be going there, but then on this side it's going in this direction, and then it's going to continue to go downward here, and then it's going to go back upward here. So that's the path that's going around the boundary. We're going to begin with the vector form of Kirchoff's voltage law. You'll remember vector form of Kirchoff's voltage law simply says that the surface integral, it's a line integral of E dot dl is equal to 0. So remember that E dot dl gives you a voltage. So if you take the sum of all the voltages around a closed loop, you get 0. Applying that to the dotted line path, we find that E sub 2t, which is in the yellow side, that's in the same direction as the path that I've chosen, but E sub 1t is in the opposite direction. You'll notice that the arrowheads right here show the direction of those fields. So it's E sub 2t minus E sub 1t times delta y. And delta y, of course, is just this distance right here, delta y. And if we assume that those electric fields are constant within each of the 2 regions, the line integral just becomes a multiplication. We can divide both sides by delta y, and then E sub 2t equals E sub 1t, probably the most useful form of that equation. But if you do prefer it in the displacement field, then equation 21.10 would be your thing. Let's then consider the tangential magnetic field, and here we're going to begin with Ampere's law. We're going to omit the displacement current here because the fields are statics, so there's no derivative. So we have the line integral of h dot dl is equal to the enclosed current. Well, this is the same sort of analysis that we just did for the electric field. H sub 2t is in the same direction as the path. H sub 1t is in the opposite direction. We'll assume that the sandwich is so thin that the ends don't really contribute anything to the line integral. But what is captured is that there is a j sub s. So I'm going to go back up to the figure here. I'm going to mention that, again, although I'm showing a 1-dimensional path here, this is still a 2-dimensional boundary in between these 2 materials. And so it's not a planar material here. It's a chunk of material. And so we're kind of looking at this boundary here. And we're saying, again, what about this region in the middle here? is it possible that something could be happening in that region that could mess up what's happening in our equations? And the answer is it's possible, although very unexpected, that we could have some current density flowing just along this two-dimensional path. And you might say, does that ever happen in reality? And I'd say, yes, sometimes it does happen in reality, but not when we're talking about the sorts of problems that we're working with. But we need to account for that. We need to account for the fact that there could be a J sub s, a surface current density, that could be flowing along that surface. And that's where we get this J sub s times delta y. So this J sub s times delta y would give us the possibility that there would be a surface current density. But in reality, there isn't. I mean, in the problems that we're working with, we're going to omit that surface current density. We're glad to know that it could impact the result, but in the problems we're working with, it's not going to impact the result. So the right-hand side goes to 0. We can then cancel the delta y. We find that h sub 2t equals h sub 1t. Or if we would rather, we can write it in terms of b sub 2t and b sub 1t. So over the course of several pages, then, we've derived 4 important results. And these important results are for the electric field and the magnetic field in the perpendicular or normal direction and in the tangential or parallel direction. And it's really interesting to me, and really I love symmetry. I love that each of the 4 variables, D, E, B, and H that we've worked with, each of the 4 variables is continuous for one of those 4 cases. So I think that this is one of those places where science is really beautiful. That although the math was done in 4 different ways, we ended up with 4 results that really complement each other. So an electric field of 20 volts per meter is incident on a boundary from air into a dielectric material with epsilon r equals 10. Let me try to draw a picture here just to give you a concrete feeling for this. Over here I have epsilon r equals 1 because that's air, and over here epsilon r equals 10. And it is incident at an angle of 35 degrees away from perpendicular to the boundary. So I'm going to draw a perpendicular line to the boundary here, and the incident wave is coming in 35 degrees away from that. So 35 degrees away from perpendicular. Now you might say, why didn't you use this equation? Why didn't you use that angle over here? Well, you'll see in a little bit. It turns out that this does give us some really good benefit if we use it perpendicular to the incident wave angle relative to the perpendicular. What is the angle of the electric field relative to the boundary once it has entered the dielectric? That should be a question mark. And we know that the incident field has a strength of 20 volts per meter. So what we need to do is we need to break this incident wave down into 2 components. We're going to have E sub t and we're going to have E sub n. And this is E sub 1t and this is E sub 1n, because on the other side we're going to have E sub 2t and E sub 2n. So I can calculate E sub 1t is going to be equal to 20 times the sine of 35 degrees. If you look at that angle, E sub 1t is the opposite from that angle, and so therefore it's going to get the sine. So 20 times the sine of 35 degrees is 11.47 volts per meter, and E sub 1n is equal to 20 times the cosine of 35 degrees, which turns out to be 16.38 volts per meter. So we've broken this wave, which is neither perpendicular, neither normal nor tangential, neither perpendicular nor parallel. We've broken it down into its components, and now we can treat each of those components according to the analysis that we just did. So we know from the previous analysis that E sub 2t is equal to E sub 1t. Let me just scroll back up and prove that to you. We have E sub 2t equals E sub 1t, and we're going to now apply that down here. And so we know that in the second material, we're still going to have 11.47 volts per meter in the tangential direction. So whatever happens to the normal direction, the tangential direction has stayed the same. E sub 2n is equal to what? Well, let's scroll way back up. And at the time I mentioned it, E sub 2n is equal to E sub 1n times epsilon r1 over epsilon r2. So we're going to apply that rule now in solving for the normal component in the second material. So we know that E sub 2n is equal to E sub 1n times epsilon r1 over epsilon r2, and that is 16.38 times epsilon r1 is 1 and epsilon r2 is 10, and so therefore E sub 2n is equal to just 1.638 volts per meter. I cut it by a factor of 10. So what we know now is that the wave is definitely going to do something like this. It's going to go down here because this component, the normal component, is 1.638 and the tangential component is 11.47. And what we want to know is, what is this angle theta 2? Well, the angle, I'll say tangent of theta 2 is going to be equal to 11.47 divided by 1.638, because it's going to be for this angle, let's see, so that angle is going to be the same as this angle right here, so that's theta 2, and so therefore 11.47 is the opposite, 1.638 is the adjacent, tangent is the opposite divided by the adjacent, so theta 2 is the arctangent of 11.47 divided by 1.638, which turns out to be 81.9 degrees. So that is a substantial change in the direction of that wave, but it's a substantial change to go from air into a relative dielectric constant of 10. You might say, well, what would have happened if it would have gotten to 90 degrees? And the answer is that we would have had total reflection. And that's something that we don't spend a lot of time talking about in this class, but we may come back and talk about total internal reflection at a later time. Okay, now that analysis, totally reasonable, not that hard, but we can do some upfront work that's going to make that analysis practically trivial. So you can see here in figure 21.3 is a more professional version of the figure that I drew up here in the previous example. What we want to do is we want to go ahead and pre-do this analysis so that we can just apply it in future cases. So we understand that in both sides, the tangential component is going to be the electric field multiplied by the sine of theta, and the normal component is going to be the electric field multiplied by the cosine of theta. Now if we combine those equations with equation 21.4, and you'll remember that 21.4 was epsilon r1 equals E sub 1 n, or E sub 1, I'm sorry, let me try this again. Epsilon r1 times E sub 1n is equal to epsilon r2 times E sub 2n. And so all we're doing is we're replacing the normal component with the total field times the cosine of theta, and on both sides. So all that's doing is making that substitution. If we applied them to equation 21.9, which said that E sub 1 tangential is equal to E sub 2 tangential, well, in that case there's no epsilons to worry about. We can divide the 21.17, that should have said 21.17 divided by 21.16. If we do that division, we end up with 21.18. And then, of course, the sine divided by the cosine gives a tangent. The E1s are going to cancel each other out. The E2s are going to cancel each other out. And I end up with a tangent of theta 1 over epsilon r1 equals tangent of theta 2 over epsilon r2. Or if I simply rearrange that equation a little bit, I get tangent of theta 1 over tangent of theta 2 equals epsilon r1 over epsilon r2. A much easier way to solve these problems, and it's a very common problem, so it's worth investing the time to derive that equation. That's known as Snell's law, and that's the law that Ibn Sahl developed more than 1,000 years ago. I think about the amount, and now he didn't derive it in the same way that we did, but he was aware of this law and had it in this form, and so that's pretty interesting. That's a very advanced work for something that was 1,000 years ago. Let's repeat that calculation from when we did it the full method. Let's repeat it now and see if we get the same result and see if it is in fact easier to work with. We know that tangent of theta 1 divided by tangent of theta 2 is equal to epsilon r1 divided by epsilon r2. What we want is that the tangent of theta 2, which is the unknown quantity, is equal to epsilon r2 over epsilon r1 times the tangent of theta 1, which is going to be 10 divided by 1 times the tangent of 35 degrees. and therefore theta 2 is equal to the arctangent of 10 times the tangent of 35 degrees, which turns out to be 81.9 degrees. And you can go back and verify that that is the same equation, or the same result that we got before. And I think you would also agree that it was significantly simpler to do it this way. So it was, in fact, worth the time to invest in that derivation. Now, the reason I mentioned to you, the reason why we go with the angle relative to the perpendicular, why do we take the angle to be here and say here, is because that way we get the cleanest form of equation 21.20. If we went with the opposite angles, we would end up with another equation that just wouldn't be quite as compact as that one. Let's do one more example. An electric field is incident on a boundary with an angle of 15 degrees away from perpendicular to the boundary. The transmitted wave has an angle of 30 degrees away from perpendicular to the boundary. The wave is moving from air into a dielectric material. What is the dielectric constant of the second material? So I know that theta 1 is equal to 15 degrees. I know that theta 2 is equal to 30 degrees. And I know that epsilon r1 is equal to 1 because it's air. So I can say tangent of theta 1 divided by tangent of theta 2 equals epsilon r1 over epsilon r2, or epsilon r2 is equal to epsilon r1 times the tangent of theta 2 divided by the tangent of theta 1. That is 1 times the tangent of 30 degrees divided by the tangent of 15 degrees, which is 2.15. So not as extreme a change, but it's not as extreme a change in epsilon r either. Just one quick reminder, if you're solving problems like this, remember that epsilon r always must be greater than or equal to 1. There cannot be a dielectric material that has an epsilon r that's less than 1, and if you do a calculation and it yields that epsilon r, then either the problem statement is wrong, because if I chose these angles poorly, I could give you a case that's not possible. I could give you a case where it's not gonna, there is no possible combination of epsilon r's that would yield that, or it just means that you've done some math error. And so just be aware of that, make a note if you get an epsilon r that's less than 1. Okay, enough about those fields. Now let's go back to the world of electromagnetic waves. So what we want to do is we want to think about what happens when we have a wave that is incident on a boundary. And so here you can see I've drawn an incident, which is just a fancy word for incoming. So when you see incident, I don't want you to think of like an accident. I want you to think of an incoming wave. So there's an incoming wave. I know that it's incoming because k sub I is pointing to the right. So it's definitely going to hit the boundary. And if I wanted to, I could confirm that, remember that we have a sub e, so the unit vector in the direction of e crossed with a sub h has to be equal to a sub s, which is also equal to a sub k. So if I put my fingers in the direction of the electric field and I curl them so that they're coming out of the page in the direction of h, then my thumb sticks in the direction of k. And sure enough, that is correct. So the configuration that we've shown here is correct for E, H, and K. Now as that wave hits the boundary, as it comes in here and it hits the boundary, part of it is going to be transmitted through and part of it is going to be reflected back. And the part that's reflected back is shown here. You can see that the K direction has changed. That's because it's now sort of pointing away from the boundary. The electric field, interestingly, doesn't change direction, and the magnetic field flips. So you put your fingers in the direction of E, you curl them into the page because X is the H is represented by an X, which is flowing into the page, and again, your thumb is going to point in the direction of K. So we can see that there's a reflected wave, and the incident wave is really, the transmitted wave is really identical to the incident wave. It's just, it has the same electric field direction, magnetic field direction, and K direction. We know that the first material has a certain epsilon r1 and mu sub r1, and the second material has epsilon r2 and mu sub r2. What we want to do is we want to study what portion of the wave is going to be transmitted and what portion of the wave is going to be reflected. This is going to take some time. It's going to take us a little bit of work. Originally, I had planned for what we're seeing today in Lesson 21, or Chapter 21, to be just half of the material that was going to be in Chapter 21. I got to page 12, and I was like, well, looks like this is the whole chapter. So the next Chapter 22 is going to pick up the second half of this material, because there's a lot that goes into these derivations. So we're going to start out by having mathematical representations of these three vectors. There's the incident vector, there's the reflected vector, and there's the transmitted vector. Each one of them is in the y direction, and each one of them is varying with z. So it's polarized in the y direction, but it's moving in the z direction. Now notice that over here I have against the subscripts a sub I, b sub r, and a sub t. So those subscripts match. And anything that is moving to the right, that's going to get a capital A, and anything that's moving to the left, that's going to get a capital B. So it isn't going to be essential to us, but it helps us to remember which waves are moving in which direction. And then each one of these terms is also, of course, has a complex exponential, e to the j omega t plus or minus k times z. Notice that the first two, which is the incident wave and the reflected wave, those are both in material number 1, so they both get k1, but the transmitted wave is actually in material number 2, so it gets k sub 2. Also notice that the incident wave is moving to the right, so that's a negative sign, and the transmitted wave is moving to the right, so that gets a negative sign, but the reflected wave is moving to the left, so that gets a plus sign. So we got a lot of different relationships here. I'm going to erase all of these marks now because I want you to be able to see clean versions of the equations. But just remember that there was a lot of thought that went into writing these equations. Similarly, we can write the H components. So these are polarized in the x direction. Again, there's an incident, there's a reflected, and there's a transmitted wave. And we're going to say that the magnitude of each of these waves is equal to the magnitude of the electric field that corresponds to it, divided by the characteristic impedance for whichever region that wave happens to be in. Remember that this wave is in region number 2, so it gets the characteristic impedance number 2. These components up here, the complex exponentials, are really identical. And you might say, well, where did these negative signs come from? Well, remember that we can determine the direction of the magnetic field given the direction of the electric field and the direction of motion. And it's this equation up here that we use to determine that. So this equation is used to determine the direction of the magnetic field. And that's interesting that we can use that information to be able to figure out what is going to be the magnetic field change. So that's where those two negative signs came from. So we now have complete versions of the equations for the electric fields and the magnetic fields, and we're now going to do some interesting things with those. One thing we're going to do is we're going to make the assumption that the boundary is at z equals 0. It doesn't have to be. Everything would be fine if we put the boundary anywhere else. It's just that this makes the math a little tiny bit easier. So what that essentially means is that each one of these terms is going to go away, and we'll essentially be left with just e to the j omega t. So all that care that we put into the plus and minus sign, all that care we put into the k1 versus k2, none of that's going to really make a difference. It would if the boundary weren't at z equals 0. So, and I should say the same thing is going to be true of the electric field. So this will go away, this will go away, and this will go away as well. So we have relatively simplified versions of those 6 equations. Now we're going to think about where do the 6 equations fit into our knowledge of what happens at the boundary. Remember that what we need is information about the tangential component in the first material and the tangential component in the second material. But the tangential component in the first material is the sum of the incident wave plus the reflected wave. And in the second material, there's only the transmitted wave. So we can write these 2 equations that allow us to sort of relate the e sub 1t and the e sub 2t. Well, remember that e sub 1t is equal to e sub 2t. So e sub 1t is equal to e sub 2t, and all we're doing is substituting equations 21.28 and 21.29 into that relationship, that e1t equals e2t. So now we have a relationship between the incident, the reflected, and the transmitted waves in the electric field. I'm going to plug in the things that I know for those 3 waves. So I've basically e sub yi becomes this one, e sub yr becomes this one, and e sub yt becomes this one. cancel out the e to the j omega t's, and I'm left with equation 21.32, which is talking about the amplitude of the incident wave, the amplitude of the reflected wave, and the amplitude of the transmitted wave. That's really helpful. We would like to know some more information about the relationships amongst those amplitudes. Let's set that aside for the moment. I put a box around it so we would remember that that's a really important equation. But let's now talk about magnetic fields. So we have the tangential component in the first material is going to be the incident plus the reflected, and the tangential component in the second material is just the transmitted wave. So once again, we can take what we know. We can say that h sub 1t is equal to h sub 2t. And so all we did was plug in, and now I've kind of combined two steps. I plugged in this on the left-hand side, so that became this, but at the same time, I put in what I knew for h sub xi and h sub xr. And then similarly, this right here became this right here. Once again, we can cancel out the e to the j omega t's, and we're left with an equation that relates the magnitudes of the fields, but now there's these characteristic impedances are mixed in because it's magnetic fields. So that's the other equation. So I've got the equation up here, which I derived from electric fields. So that's equation 21.32. That one deserves some extra special attention. And then we have equation 21.36, also deserves extra special attention. And if we use those two equations, we can derive this equation right here for the reflection coefficient. The reflection coefficient is simply the magnitude of the reflected wave divided by the magnitude of the incident wave. So how strong is the wave that gets reflected as a ratio of the amount that comes in? You know, if we had, let's imagine that A sub I is 10 volts per meter and B sub R is 7 volts per meter, well then gamma is 7 divided by 10, which is 0.7. 70% of that wave would get reflected. But we can actually calculate that for any given material if we know the characteristic impedances. Now I kind of made a pretty big jump there, but I want to show you how to get from one to the other. So we're going to start with equation 21.32. Just want to remind you that A sub I plus B sub R is equal to A sub t. That's equation 21.32. We can then divide both sides of equation 21.32 by both sides of equation 21.36. So this is A sub I divided by Z sub C1 minus B sub R divided by Z sub C1. And on the right-hand side, it's A sub T divided by Z sub C2. Well, the best thing that doing that does for us is that it's going to eliminate the A sub T. So A sub T's are going to cancel. Now the only variables that are left, if we assume that we know the characteristic impedances, the only variables that are left are A sub I and B sub R. And our goal is to find the ratio between those two. Well, I have Z sub C2 in the denominator of the denominator, so it moves up to the numerator. And now I'm going to multiply the denominator of the left through so it moves over to the right-hand side. So I get A sub I plus Z sub C2 times A sub I over Z sub C1 minus B sub R over Z sub C1. And, oh, no, that's not, hold on a second. Nope, that was a mistake. It's A sub I plus B sub R is equal to Z sub C2 times A sub I over Z sub C1 minus B sub R over Z sub C2. Now let's concentrate on the right-hand side, and I'm gonna separate this so it's A sub I times Z sub C2 over Z sub C1 minus B sub R times Z sub C2. Oh, that's a mistake. Sorry, this should have been Z sub C1 divided by Z sub C1. Now I'm going to put all the AI's on the left and all the BR's on the right. So AI times 1 minus Z sub C2 over Z sub C1. And then on the right, I'm going to get minus BR, you know what, I'll just write this as minus BR times 1 plus Z sub C2 over Z sub C1. And now I'm going to take the ratio of B sub R divided by A sub I. So a sub I is going to move over here, and this term is going to move over here. So I get b sub r divided by a sub I is 1 minus z sub c2 over z sub c1 divided by negative 1 plus z sub c2 over z sub c1. I'll multiply the numerator and denominator through by z sub c1. I get z sub c1 minus z sub c2 divided by negative z sub c1 plus z sub c2. And then I'm going to move the negative sign from the denominator up into the numerator, and because that's a subtraction, I can simply flip them. And so I say gamma is equal to b sub r over a sub I, which is z sub c2 minus z sub c1. I flipped the two terms in the numerator, which brought the negative sign up into the numerator, divided by z sub c1 plus z sub c2. And so happily, that is in fact the same result. It didn't take that much work, but I just thought that it would be more interesting to work through it this way rather than see the equations typed out. Now the transmission coefficient can also be found, and the transmission coefficient is 2 z sub c2 over z sub c1 plus z sub c2. Not going to derive that one, but I think that you'll probably take my word for it. Remember that we have an equation that relates z sub c to the mu's and the epsilons of the materials. And so if we applied that equation, and if we assume, let's make the assumption here that mu sub r1 is equal to mu sub r2. Because typically we're talking about dielectric materials here, and no dielectric materials also happen to be ferromagnetic materials. So if we assume that they're both equal to 1, then we can omit those, and then what we're left with is equations for gamma and t, the reflection coefficient and the transmission coefficient, strictly in terms of epsilon r's. And again, it would have taken a little bit of extra algebra to get there, but it's not too bad. And then finally, the transmission and reflection coefficients are always related by that equation. So t is always equal to 1 plus gamma. That's a really good way to check your answers. I made a mistake in one of the examples you're about to see, and I was able to catch it because I knew that that third equation was true. So we have an electromagnetic wave moving from region 1, which is free space. So right away I know that epsilon r1 is equal to 1, into region 2, which has a relative dielectric constant of 4. Calculate the reflection and transmission coefficients. So gamma is equal to the square root of epsilon r1 minus the square root of epsilon r2 divided by the square root of epsilon r1 plus the square root of epsilon r2, which in this case is 1 minus 2 over 1 plus 2, which is going to be negative 1/3. That's right, it's negative. So realize that the reflection coefficient can be positive or it can be negative, and it will basically you're talking about did the direction of the electric field flip. So just be aware of the fact that we're talking about the direction here did in fact flip in spite of what the original picture that we had showed. And then t is equal to 2 times epsilon r1 divided by epsilon r1 plus epsilon r2, which is, in this case, 2 times 1 divided by 1 plus 2, which is 2/3. And if we do our check, t equals 1 plus gamma, yes it does. 2/3 equals 1 plus negative 1/3. Now let's consider what happens if we're going the opposite direction. What if we're going from the dielectric? So epsilon r1 is equal to 4 and epsilon r2 is equal to 1, going from the dielectric into free space. So now gamma is going to be equal to the square root of 4 minus the square root of 1 divided by the square root of 4 plus the square root of 1. That gives 2 minus 1 over 2 plus 1, which is positive 1/3. And when we're talking about reflection coefficients, sometimes I will put a positive sign on there just to help clarify that I didn't forget a negative sign. And then t is equal to 2 times the square root of 4 divided by the square root of 4 plus the square root of 1, which is 2 times 2 over 2 plus 1, which is 4/3. Phew, that was the sound of my mind getting blown, because it seems that the transmitted wave carries more amplitude than the original wave did. And don't worry, conservation of energy will still hold. We're not quite to the place where we can prove conservation of energy yet, but trust me when I say that yes, the amplitude is greater, but the energy will be the same. I'll say the energy in the transmitted wave is equal to the energy of the reflected wave plus the energy of, sorry, my mistake. The energy of the incident wave gets shared between the reflected wave and the transmitted wave. We might write that as energy, we might write it as power, but we will come back and see that conservation of energy holds. For now, just be aware of the fact that gamma can be positive and negative, and T can be positive and negative, and they can also each be greater than 1. Calculate the amplitude of the electromagnetic waves that are reflected and transmitted when a wave with an amplitude of 10 volts per meter is incident from air into a region with epsilon r equals 10. So epsilon r1 equals 1, epsilon r2 is equal to 10, and a sub I is equal to 10 volts per meter. So we can first of all calculate gamma. Gamma is the square root of 1 minus the square root of 10 divided by the square root of 1 plus the square root of 10. When you plug that into the calculator, you get minus 0.519. You might be tempted to just say T equals 1 plus gamma. I would encourage you to do the calculation. 2 times the square root of 1 over the square root of 1 plus the square root of 10 is 0.481. And when you do that calculation, you can now confirm that you did both of the calculations correctly by using T equals 1 plus gamma to check your results. And when you do that, this does in fact check out. So I know that the reflected amplitude is equal to the reflection coefficient times the incident amplitude, which is minus 0.519 times 10, which gives me minus 5.19 volts per meter. You might say the amplitude shouldn't include that negative sign. If you want to omit the negative sign, that's fine. I've included it here just so that we can see that it is in fact going to be flipped. And then the transmitted amplitude is going to be equal to T times a sub I, which is 0.481 times 10, which is 4.81 volts per meter. And so you can see that it's about half and half. It seems like omitting the negative sign there or ignoring it for the moment, it looks like about half of the wave is getting reflected and about half of the wave is getting transmitted. And it's a pretty substantial change from epsilon r equals 1 to epsilon r equals 10. So I'm not surprised that it reflects so significantly. So, summary for today. At a boundary between materials with different values of epsilon r and or mu sub r, we have to consider the normal and tangential components separately. And we have to consider the electric and magnetic fields separately. If we assume that there's no surface charge density or two-dimensional current density, those are important assumptions, but very reasonable ones, then we end up with a table that shows which of the variables is continuous across the boundaries. We can use those relationships to derive Snell's law, which is misnamed. And then when an electromagnetic wave is incident at a boundary between two regions that have different values of epsilon r, we can calculate the reflection coefficient in one of two ways. We can calculate the transmission coefficient in one of two ways. Most typically in this class, we'll know the values of epsilon r, but quite often in the real world, you would actually have two pieces of cable, and you would know the characteristic impedance of those cables, or two different materials, and you could easily calculate the characteristic impedances. In that case, then a sub I, so this a sub I right here is the amplitude of the incident wave, and b sub r is the amplitude of the reflected wave, and a sub t is the amplitude of the transmitted wave.